Hello, and welcome to this new series in quantum mechanics, where we will be looking into the deeper concepts therein using graphs and linear algebra, a way to introduce ourselves into quantum mechanics. We have already seen the vectors and the properties and the attributes of the vector in the previous series on linear algebra. And that information about vectors will also help you try to now correlate the concepts of quantum mechanics. So let's get started. To begin with, it is important to understand the concept of states and how it is related to vectors. So what is a state? An state can be defined as a condition of a person, a thing or object with respect to the circumstances or the attribute that defines it. For example, traffic light at a given moment of time can be in different colors like red or green or maybe amber, but it cannot be at the same given time in two different colors. That would lead to a very dangerous situation on the road. Thus, on a low voltage in our classical computing is abstracted, rather the abstraction is created by us to be called as a binary value of 0. The high voltage subsequently is marked as 1. As you know, classical computing is based on bits which only hold two values of 0 and 1. We can also extend the states having different attributes giving information about something. For example, a car is a fast car with having probably a high power fuel cylinder, but also it's defined at the same time with its color, which is blue. Therefore, it is important to understand that the states are informing about the object, but the same information can also be stored as a states too, thereby making correlation. So if you say that today, if it's rain and if the temperature is below certain degrees, I'm gonna drink hot chocolate. So that's the correlation and that's the information being stored in states meant. Let's take an example. Consider that you have four vertices with like no edges, and each vertices is holding number of marbles which are indicated by the actual number written in those vertices like 1, 3, 4 and 5. This represents an state which can be represented by a vector. As such, the vector will read in order of the indices how the vertices are represented: 5, 4, 3, 1. However, if you think of it, if you split this vector representation into this vector configuration, you will end up in something like this. So each vertices correspond to a base vector, and each coefficient then represents the vertex itself. It is important to note that the space vectors are orthogonal with respect to each other. And what is orthogonality? We have seen in the series of linear algebra. So this can be written this way. However, writing this in an extended form is quite cumbersome. We are at this point of time talking about four vertices, but imagine that if you have thousands of them writing in the linear combination of base factors would be certain extent impossible. Therefore, it is important that we pay attention to the coefficients which represents each vertices. Therefore, we can take vector of coefficients which makes up the linear combination, and this precise vector represents the state of that system. You can therefore safely write the vector as combination of coefficients, assuming that each coefficient representing a base factor are and represent those base factors which are orthogonal to each other. Therefore, we only care about the coefficients. You can extend this concept, as I said, to any number of coefficients. So for example, if you have more than 100, 200 or 500 coefficients, this distribution of coefficient can still help you formulate that factor which represents the state of system with more number of coefficients. For it is important to understand that this marble distribution, that what we have seen here over the vertices, is a state of system which we can easily describe by a vector using coefficients of each vertices. I'll stop here. Thanks for watching, and I'll see you in the next video. Thank you very much.